Hello everybody, in this lecture we will be solving 1975 IMO problem number 4. Here is a view of this problem. When 4444 raised to the power 4444 is written in decimal notation, the sum of its digits is A, and let B the sum of the digits of A itself, and finally the sum of the digits, finally we are to find the sum of the digits of B. And you can call that number C if you want. I won't call it anything. But for the time being, let me call the number, the original number, as X. So let X be equal to 4444 raised to the power 4444. And we would like to consider the sum of digits of that number. So the sum of digits of X would simply be A, right? So let's write that down. A is sum of digits of X itself, versus B itself is sum of digits of A. And finally, the question doesn't even bother asking for B, but it's asking for the sum of digits of, sum of digits of B itself. So there's a very well-known result. So you guys all probably know from elementary school that a number is divisible by 9 if its sum of digits are divisible by 9. What it means is it translates into the following lemma, I would call it lemma. So for all n positive integers, we would get that the number n is actually congruent to the sum of its digits, and that happens in mod 9. Okay, so this everybody knows. This is a very well-known lemma. In fact, let me just take a few minutes to prove it. And this lemma is closely related to divisibility by 11 rule as well. The logic is very similar. Sorry for that. For the proof of this result, consider a number n, which in its decimal representation, let's say, is written as d k plus 1 d sub k d sub 2 d sub 1, and this is the decimal representation of this number. Interestingly, well, we can write it, because we know this is a decimal representation, we can expand this in the usual way. So that's simply equal to d1 plus 10d2 plus 100d3 plus all the way up to let me put some more space here, all the way up to 10 raised to the power k d sub k plus 1. But then we can further split these things. I need more space, so let's continue from here. So d1 plus, I'm gonna go ahead and split this as d2 plus 9d2 plus, and I'm gonna split this one as d3 plus 99d3, and finally I'm going to split this one as d sub k plus 1 plus 10 to the power k minus 1, 10 to the power k minus 1 d sub k plus 1. Now, in fact, I can reorganize these things. Obviously, I have d1 plus d2 all the way up to d sub k plus 1 plus, and then for the remaining terms, I just observe that all of them is divisible by 9, including this one. So I will just factor out the 9. So we would just have a d2 plus 11d3, and so on. 11d3, and for the last one, d sub k plus 1 will have 1 1, a bunch of ones. I believe there should be a k ones, k, or I think there are k ones here, k ones. d sub k plus 1. Well, it doesn't really matter, because now I just realized that this whole thing is a multiple of 9. Multiple of 9. As a result, this whole thing, expression, let's go back. So this implies that n itself, when you take it in mod 9, that's simply this part, d1 plus d sub k plus 1. And notice that this guy is just this part is just 0 in mod 9, right? So that's it. So we have our expression, which is simply the sum of digits of our number. Now, having proven this result, we can now confidently go back and look into our problem. So let's calculate x in mod 9, and that would give us a clue about what a and b can look like. So let's start with 4444. So this number in mod 9 apparently is congruent to, using our lemma, we just check the sum of digits, which is 16, which is congruent to 7 in mod 9. So therefore, when I before I do further trick, let's further consider this one, raised to the third power. Why do I do that? Because I just realized that yeah, this is just equal to 7 cubed, but 7 cubed in mod 9 is just congruent to 1. So therefore, having evaluated 4,000, the exponent is 4,444, dividing it by 3, 14, 4 times 2 remaining 24, 8 times 0 remaining 4, 1 time, and then we have a 1 remaining. So therefore, I can express the original number x, which is this, in the following manner. So that's simply congruent to 4,444 raised to 3 times 1481 plus 1. But that's simply, yeah, we can just do it like this, if you will, and then split the one of those numbers. And finally, so that's simply congruent to 1 raised to the power 1481 times, and 4444 is just equal to 7, congruent to 7 in mod 9. When you multiply these, we would just get that x itself is congruent to 7 in mod 9. But now it's time to apply our lemma, which says that x is congruent to 7, implies that a itself, the sum of its digits, will also be 7, and then the sum of digits of a itself will also be 7, and that's also the sum of digits of b in mod 9. So this follows, so this is a repeated application of our lemma. So we have used our lemma earlier here, but we repeatedly keep applying our lemma here and here as well to get this result. So therefore, now I have more or less an understanding of what's going on. I will now find an upper bound for x, for the number x, and hopefully upper bounds for a and b as well as the sum of digits of b, and then that will pin down the potential values for the sum of digits of b. So let's go ahead and do that. But I first need to find the number of digits of x. To do that, I would just take the logarithm of x. So therefore, logarithm of x, which is equal to logarithm of 4,444 raised to, this is a huge number, obviously. That's equal to 4,444 logarithm 4,444. But that's decidedly less than 4,444 logarithm 10 to the power 4 to 10,000. Well, this is nice because that's simply 4 times 4,444 times logarithm 10 in base 10, obviously. So that's just equal to 1. So that number is just 17,776. So therefore, the logarithm of x is less than this number, recall the less than sign, implying that x has at most 17,776 digits. But then I can speculate in the following way: even when all the digits of this number is 9, so the max sum that the digits of x can take, the sum of digits of x is a, obviously, so the maximum value that the sum of digits of x can take, so the sum of digits of x, I mean, is a, right? So the maximum value that a can take is, if all these digits were a 9, that would have been the answer, right? So 17,776, and this is simply 159,984, if I'm not mistaken. So therefore this implies that a is less than or equal to that number. So let's clean that up. So a is less than or equal to 159,984. But then when you look at the numbers less than 159,984, the one with the maximum sum digits, right? Maximum sum of digits number less than this bound, less than or equal to 159,984, is simply 99999. So therefore, so this is a potential candidate for the number a. We can call it a max, and the sum of digits here, sum of digits is 45. So therefore this gives me an upper bound, so this implies an upper bound for the number b itself. So b cannot exceed 45. But then working backwards again, what is the maximum number, what is the maximum sum of digits? Let's write that down here again. Maximum sum of digits number less than 45, less than or equal to 45. It turns out that the maximum sum of digits number less than 45 is just, so 39 has the maximum sum of the digits from any given number b. So as a result, the sum of, let's write that down so far, the sum of digits of b at most would be at most 12. Now the question, going back to our problem, we need the sum of digits of b. We know that an upper bound for the sum of digits of b is 12, but at the same time, if you remember very early on, I established that it should be also congruent to 7. So there is actually only one single number less than 12 and congruent to 7 in mod 9, and that's 7. So therefore this implies that well, obviously 0 or 7 would work, but it can't be 0, right? So we are considering a number. Of course, the sum of digits of a number would never be equal to 0, so that would definitely be equal to 7. 7 would be the sum of digits of b, and that solves our problem. Hope you enjoyed it, and looking forward to see you guys in our next lecture.